In the last video, we began discussing how to interpret a vector field geometrically, and we focused on the 2D case. Now we're going to focus on the 3D case. So remember that in 3D vector fields, the curl was a little bit more expansive of a, of a quote-unquote formula, but really remember it's just a determinant. And then when we think about it, at least from what we were saying before back in the motivation video, we think of the curl describing microscopic rotation around in a little ball around the point of interest. Okay, so now geometrically, what we see happen is that quantity nx minus my, so that third component, that's going to describe rotation that is perpendicular to the z-axis. Remembering that the z-axis is spanned by the unit vector k. And then py minus nz, so that's the first component, perpendicular rotation to the x-axis, and then to the y-axis for the last one. Okay, and so if we focus on maybe just py and nz for a moment here. Py, so that is saying how the vector field changes vertically, and so if we think of py as positive, okay, so here what we would see is that if py is positive here, that means we're going to induce, at least in this case, so as we progress in y, the length of the vectors are getting longer, right? So that's going to induce counterclockwise rotation. And then similarly, if we look at nz and say nz is negative, okay, so as I go up in z, let me undo that. Why don't we do this in something a little bit darker? Let's try black. So if I say nz, so let me just go back and clarify here. Py we're saying is greater than 0, and then just to make sure that we end up with counterclockwise rotation here, if I say that the nz here is negative, then we're going to get counterclockwise rotation as well. Okay, and so when we think of this counterclockwise rotation, it is rotation, since we're in the YZ plane, it's rotation in the x-axis, or perpendicular, I guess, in the y-axis. Okay, y-axis, or sorry, x-axis is the rotation that's perpendicular to that. Okay, all right. And then here, just as we did with 2D, it's wise to look at the sign of the components. Okay, and largely what we're going to see is the exact same thing. So if we have positive components, then we're going to have counterclockwise rotation. If we have negative components, we're going to have clockwise rotation, and then 0 is going to be irrotational again. Okay, irrotational. Okay, and so the sign of the components is going to describe microscopic rotation in 3 directions. Okay, so you may have to describe, so I should also clarify that you would say that there's clockwise rotation in this component, but counterclockwise rotation in that component. So it does get a little bit more complex, and perhaps hard to visualize at times, but you could have easily combinations of these rotation directions. Okay, and before, when we looked at the length, or at least the absolute value, but which turned out to be the length of the curl, we said this was the speed, and that's not going to change when we go into three dimensions. Speed of rotation. And then when we look at the curl, when we look at that direction in particular, this is going to give us the axis of rotation. Okay, knowing that the axis kind of follows the right-hand rule. Okay, so what you would do is you'd have to determine kind of the direction of the curl, put your thumb in that direction, and then the fingers would rotate in the direction of rotation. So if you can imagine, I'll just draw a quick little picture. Okay, so here's our little ball, okay, and you have this vector here as the curl vector. So you would put your thumb in this direction, and then your fingers would sweep around the ball in this direction in a counterclockwise as viewed from the top of this vector. So it's kind of interesting. Just make sure to do it correctly. But anyway, time for an example. Okay, 3D vector field. Okay, we want to find the curl. So I want you to pause the video and do it yourself. And so here's what I got for the curl, minus y minus z minus x. Okay, and then kind of going through these other questions about the axis of rotation. Now, previously we said that the axis of rotation was going to be the del cross f, right? So that's technically true, but when we're describing the axis, it's all kind of scalar multiples of that. So what I would say here is that instead of saying that it's minus y minus z minus x, really, since they're all a kind of values that are changing the same, I would say that the axis of rotation is excuse me, minus 1 minus 1 minus 1. Okay. You can also list minus y minus z minus x, and that'll be okay too. Okay. For part C, if we project a sphere onto the xy plane, is this rotation clockwise or counterclockwise? So this one's a little bit more interesting. For this particular example, I think it works out okay. And so if we do that projection, okay, I think you could safely say, even before thinking of the projection, there's a whole lot of clockwise motion going on here because we have negative components, right? So really, first, just by looking at negative components, we can say it's going to be clockwise. Otherwise, we're kind of thinking, okay, well, if we were to project this into just x and y component, or to xy plane, then the third component in z diminishes, but that's actually going to describe our curl, right? Because we would say that the curl is going to be in that dimension, so all we would have to do is really look at this third component for the xy plane, and say, okay, well, since that's negative, or at least we're going to get a so it's kind of interesting that if x is positive, the curl is going to be if x is positive, the curl is going to be clockwise, and then if x is negative, it's going to be counterclockwise. Sorry, yep, that's right. So it generally, so we could, I guess that isn't a bad way to break it down too. We could say say it with that. So clockwise if x is, excuse me, greater than 0, and counterclockwise if x is less than 0. Okay, and then irrotational if x is equal to 0. All right. For the speed, remember that's the length of all this, and so what we end up for speed is x squared plus y squared plus z squared, square root. Okay, and so all this is really telling us is if we're thinking about a general description, it's going to move faster as we get further away from the origin. Ooh, so that's kind of all we have to say, and that's what I would write, but I'm going to leave that up to you. Okay, so I think we're finally done with the geometry of 3D vectors. It gets a little bit more complicated because we have more directions to think about. Okay, um, and so you got to keep in mind the components, keep in mind speed and axis of rotation, and kind of how to think about curl. Using the right hand rule, and then in this last example, the curl algebraically is easy. The axis of rotation is again anything that's kind of parallel to what you find for grading the del cross f, and then the rotation is kind of interesting to think about, and you might have to do cases as we did here. Okay, so in the next video we just have some wrap-up theorems which will go quickly. Alright, so look for those.